So far we have looked at pointers directly as ways of accessing the memory of a computer, and now we would like to sort of look a little bit more into the relationship between pointers and variables. So a variable can just be thought of as a named address, right? So when I declare something, for example, as int a is equal to 10, the int over here is the data type. It tells me what kind of data I want to store. A is a name that I give to that data type, or no, to the value that I want to store, right? It is not to the data type is always called int, right? A is a name of one particular instance of that data type, it is one particular integer, right? And the reason I give it a name is I might want to use that value in multiple locations throughout my program. Along with declaring the integer, I could also do an initialization, which is give it a value, right? And this 10 over here is the actual value. So what happens when the compiler comes across a statement like this is that it actually figures out what memory it has access to, picks some location which we cannot predict in advance, says I will use this in order to store A, and from that point onwards this name A now becomes an alias for the address in which this particular value is stored. And what does the compiler do? Because it has already got the initialization, it takes that value 10 and puts it into that particular memory location, right? Now what this means is there is a name, there is an address. I can use ampersand A in order to actually get the address at which it is stored, and by doing star of ampersand A, I will get the data value stored at that particular address. And the interesting thing to notice, the star ampersand A is pretty much by definition what A is. Okay, so if A has been declared as an int, ampersand A gives me a pointer to an integer, star ampersand A dereferences that. It knows that ampersand A is a pointer to an integer, so it returns a value of type int, and that's exactly what you get out here. Okay. So this name to address mapping is sort of the core idea behind what we are trying to do with pointers, right? This is a small snippet of code that shows that I can basically declare an integer variable, I can declare a pointer. Now I can take the address of A and store it into the pointer, right? And if I want to actually print out the value of that pointer, what I need to do is I actually need to take this pointer, which is an address, convert it into a number that can be printed, which I do using this particular syntax, right, where I give within parenthesis out here the word unsigned long. Why unsigned long? Couple of things to keep in mind. A pointer is 8 bytes wide on a 64-bit machine, so is long, right? So a pointer and long data type are of the same size, but since a pointer is actually an address, it doesn't make sense to think of a negative value for a pointer, which is why I tell it to take this 8-byte value and treat it as an unsigned number and print it out, so I can actually see what the address looks like. Okay. This notation over here, by the way, this syntax is usually called typecasting. What I am doing is taking something which is a pointer and telling the compiler to treat it as something else. I am not changing the value, I am only sort of taking the value and looking at it in a different way. Now this typecasting can actually be done in slightly different ways, right? So you might, for example, at some point in a program, you might actually even have come across something like this, where I declare float x is equal to 3.14 and I want to round it off to an integer. How do I do that? I basically declare an integer variable y and say take the int value of x. Okay. So it's the same notation that we saw earlier. I take the variable name x, I put int within parenthesis in front of it. What that tells the compiler is take this value 3.14, round it off to an integer, actually modify the value in some way, right, and assign that to y. So this is a slightly more advanced form of typecasting. What it's doing is it's actually even converting the value that you have. A 3.14 is actually going to get converted into 3 over here, right? On the other hand, what if I said x is equal to 3.14 as float, but then I say that y is a int star, okay, so it's not an integer. I just want something which is going to take this 32-bit floating point number and look at it as an integer, right? This does not do a data conversion. It does not, for example, take 3.14 and round it down to 3. It takes the 32-bit value that we have for the floating point number and just treats it as an integer and prints out that value that you have out there, right? So I have a simple program out here where I call a function which basically declares float x is equal to 3.14, and then I print both the float value of f and I take the value of x, cast it as an integer and print its value out here, right. So this, you can see what it has done is it has taken the 3.14, converted it into 3, treats it as an integer and then prints it out. Now let us look at the second line that I have out here. What I have done in this case is, I will just push it down to the next line so it is more readable. I have almost the same thing, right, except that after printing out the value of x, I then go through some fancy looking syntax out here. Let us try and interpret what this is saying. It says take x, which is a floating point number, take the address of x, but now treat that address as a pointer to an integer and take the star of that, which means dereference it. In other words, read out the 4 bytes that are present at that address location, but now instead of treating them as a floating point number, treat them as an integer, right. And this typecast is probably unnecessary, right. In fact, I could do away with this last bit out here and it should still work. What ends up happening is it prints this number out here. Now what is this number? This has nothing to do with 3.14, or at least it does not look like it, right. To understand that, let us look a little bit more closely at it by printing it out in hex, right. And now we actually see that it actually has this number 4048 F5C3, still does not seem to make much sense until you actually unpack this as a 32-bit integer, a 32-bit binary value, and then try and interpret it as a floating point number. The first bit is a sign bit, it is 0, so it is a positive number. The next 8 bits correspond to the exponent, right. So there is some 100 something, you unpack all of that and perform the computation, you will find that it actually corresponds to, effectively 2 power 0 or 2 power 1 in this case, right. And the remaining bits are what is called the 23 bits are the mantissa, right, which actually sort of tells you that this is something close to 3.14, right. It will be probably something like 1.57 something into 2 power 1 is what is ultimately being represented out here, right. So this whole business where we sort of split things up and try to do the typecasting after taking the address directly is a way by which I can take the same location in memory and then interpret it in a different manner altogether, right. I could do this with other things as well. I could, for example, take a set of characters, right, that I define one after the other, and treat it as an integer, right? So if I just take the character, I define a few characters H, I and so on, right? The ASCII code corresponding to capital H is the number 48 in hexadecimal, right? So when I print this out and just say treat A as an integer and print it out, this is what I get 48 hexadecimal. But what happens if I actually ask for something more than that? I can actually get the ASCII characters 48, 69, 21 corresponding to the H, I and the exclamation mark, and finally a 0 corresponding to the D is equal to 0 that I had, right? And it also prints out the addresses, and you find that it's basically F, E, D and C. So in other words, even though I declared A first, B second, C third and D last, the addresses start with A having the highest address, then the next B, C and D has the lowest address, right? What I could do is take the address of D, treat it as an integer and actually print that out, right? And it ends up giving me a number corresponding to an integer which is basically these 4 bytes, right? So if I take these 4 bytes and print them out, in fact if I do that and print it out this way, I find that the integer value has the hexadecimal equivalent 48692100, which is exactly the combination of the 4 characters that I started out with, right? Long and short of it, it's the same story again. All that I have is a pointer into memory. I either treat it as a set of characters out here, or I take the pointer, change the way that I am going to look into the memory, make it an int star and dereference it as star p, right? And I get the value in a different way, right? So as long as you keep in mind that all of this pointer business is just always dealing with the same data sitting in memory, and it's just a question of changing the way that you look at it, you should be able to sort of work through what is actually happening when you manipulate pointers in some way. Now when we talk about variables, there is one more aspect to keep in mind, which is about where do variables get allocated in the memory of a system, right? And for that, what we need to think about is this big outline that we have over here is the total memory available to a computing system. Now when I run a program, some part of that gets allocated to that program, right? It's usually some subset of the memory because other parts of the memory are being used by the operating system, by other programs that are running on the system, and maybe some of them are just left free, right? Some memory locations are just left free. But this smaller box can be thought of as the memory allocated to the program itself, right? Now what we do is, as we have already seen, the program that I am talking about usually starts with this function called main, right? And we have already seen that, like in the case of the recursion example, whenever a function is called, some amount of memory is allocated for that function alone and is called the stack frame corresponding to that function. So the first thing I have is some subset of my memory is the stack corresponding to main. Let's say I had another function, that function would in turn get another stack, but only when it is called, right? Remember that the stack frame corresponding to a function is allocated when the function is called and disappears when the function is exited, right? But if I had main which called func1 and then that in turn called some other function and that in turn called some other function, I would end up having stacks growing this way, right? At some point though, what we say is there is another chunk of memory that I am going to keep aside and say this is something called the heap, right? And that if I sort of keep growing the stacks this way and they end up colliding with what I have set apart for the heap, I could actually run into problems. My program can have an error, or a memory constraint violation, and it would end up crashing, right. So for that to happen, of course, usually sufficient amount of memory is allocated that does not happen very easily, but it could potentially, theoretically at least, happen, right. So this, why is this heap even needed? Because there are certain variables that need to be accessed by multiple different functions out here, right. I can't declare it inside the stack of any one function because that will go away when that function exits. So instead I declare global variables, static variables which are very closely related to global variables, and another thing called dynamic memory, which we will see later, right, using the malloc in order to allocate memory. All of that ends up going into this other section of memory called the heap, right. Again, for our practical purposes, all that matters is whenever a function is called, that function gets a stack frame. Apart from all the stack frames that are present, there is some part of the memory that is set aside for this thing called the heap, which is where the variables and data that are common across the different functions get stored. And of course, all of this is only the data. There is also some part of the program or memory that is used for storing the program instructions itself, right, and that I have sort of left out over here, but yes, that will also be accommodated. So let's take a look at some examples of how we can visualize where a particular variable goes into the memory of a system, right. It's of course a bit hard to do in general because, like I have already mentioned, every time you run a program, the addresses of variables change, right. So you cannot really look at a particular address and say, okay, this corresponds to this variable, because the next time you run the program, it would have changed. But on the other hand, there are some patterns that you can sort of make out, and in order to understand more than that, you would actually need to go deeper into how the operating system works, which we do not want to at this point, right. Anyway, to start with, what we are going to do is, the first thing I am showing out here is I declare a variable called a, but notice that it is declared outside of all the functions. What does that mean? It means a is a global variable, right. So potentially it is accessible anywhere. But then I have another function which I am calling just func int of n, and what this says is, if n is, I am writing it in such a way that I could potentially have a recursive call to this function. I basically say if n is less than or equal to 0, then just return, else I am eventually going to call func of n minus 1 after printing out what the address of a, right. I basically take the address of a and print it out inside the function, okay. But notice that I have actually declared another int a over here. So there is an int a on line 87 out here, there is another int a on line 92, right, and it looks as though there is potentially which a am I going to be accessing out here, right. We will take a look at that, okay. So let us start with that, and I am going to comment this part out for now. First things first, let us look at what happens if I just run this, right. What you can see is that the first time around I am asking for the address of a. What does it do? It basically takes the global variable, because that is the only one that exists at this point, right. This int a on line 105 does not exist when I do this printf. So when I give and a over here, I am actually going to take the address of the global variable. And as you can see, it starts with some 00 something, which looks like it is one of the lower locations in memory. Remember the diagram where the heap was something that starts from low memory and grows upwards, whereas the stacks are things that start at high memory and grow downwards, right. So the heap, in other words, seems to be somewhere low in memory, right, which is why it has an address like this. On the other hand, the moment I declare this int a, this is something which is inside the stack frame of this demo ptr locations function, and when I look at it, the top function, the address has changed completely from what it was earlier, right. From this point onwards, because a has already been declared, I can't really get back to the global variable without somehow being able to take this int a out of scope, right. So I can't really do that in an easy manner. So yeah, it turns out that I can't really get this done, right. Now one thing to keep in mind, you might be tempted to think that I can take this address and subtract this address and find out what's the total amount of memory available for the system. No, it doesn't work that way, right? It's not that this is actually a consecutive set of memory locations. This all uses something called virtual memory, which is managed by the operating system. And what happens in that case is that you have certain blocks of memory that are allocated in a certain way, but there are no guarantees about what the actual values of addresses are going to be, right? Alright, so the first thing that we could notice over here is when I run this, A has an address that I can access right away because it was declared as a global variable, but the moment I declare a new int A, that shadows or covers the global variable. From this point onwards, when I refer to A, I am referring only to the locally defined one, right? Because if I ask for the address of A, it tells me only the local address. I cannot in fact go back and do this unless I had taken this global address somewhere, stored it in a pointer, and then I tried dereferencing it. That's still okay, I can do it, but it's unnecessarily complicated. Ideally, I shouldn't be having a global variable and a local variable with the same name at all in the first place, right? But it can happen. You could come across code that actually does stuff like this. Alright, so now what happens if I actually call this function, right? What I am doing inside the function is once again declaring yet another A, right? Now let us see what happens when I do that, right, and run this. What you can see is that address of A inside the top level, that is to say inside this demo PTR locations, is one value ending with 85C, but the address inside this function, right, over here is yet another value, something ending with 834, okay. In other words, this int A that I have out here and this int A that I have out here and the int A that I have declared as a global are three different things, okay. Interestingly enough, if I comment this out, I do not have a declaration for A, right, and I run this, what do you expect is going to happen when I print the address of A inside func? Let us take a look, right. It went back to the global, right, because the global variable int A over here is accessible from everywhere, right. So, whether I have it inside this, whether I call it inside func, get the address out here, or inside the top function, that is demo PTR locations, I get exactly the same address, right, this 4014, right. This other one though, this int A that I have out here, there is no straightforward way for me to access it inside this function. It's in a different stack frame, it's not something that I can access easily, okay. Now, what happens if instead of func1 I call this as func3 instead, right? Let us go back quickly, look at the function itself. What it says is if n is less than or equal to 0, it will return. Otherwise, what it will do is it will print the address inside the function and then call func with n minus 1. That is good because as long as n is some positive number, it will eventually terminate. That is the good news. Let us see what happens when I run it, right? So, first thing it says is when n is equal to 3, inside the function the address of A is something ending with BA4. When n is equal to 2, it is something B84. When n is equal to 1, it is address B64, right? Each time, in other words, I get a different address. This is just like the recursion, right? Every time a new stack frame is being allocated for the function call, and therefore this variable int A is going into a different place each time, right? If I run the same code again, you will notice that the addresses all changed. It became 344, 324, 304, different from what we had seen earlier, right? And the point is, it does not matter, you do not have any guarantees on what the addresses are going to be. All that you can say is that every time I call the function, another stack frame is allocated, and yes, there is sufficient place for the variables required by that function. So, how we manipulate, or rather how we declare variables decides where in the memory of the system they go. Anything which is declared inside a function pretty much goes into the stack frame of that function, Anything which is declared as a global or a static variable or dynamically allocated goes into the heap generally, right. The ones that are on the heap are accessible inside all the functions. The ones that are inside a given function cannot easily be accessed by other functions, basically because there is no name pointing to them, okay.